Hello and welcome back to Differential Equations, section 5.2 on the eigenvalue method for homogeneous systems. This is where we learn the way to solve those systems of differential equations that we talked about before. And obviously this will be later made more interesting when you have the forced systems called non-homogeneous systems, right? That's going to be added much later, I believe 5.5 or something like that. We have to deal first with the basic approach. So we have the standard stuff. You have your differential equation, which will give you that, which you can write as that equation with matrix. So if you have x1 prime to be a11 x1 plus a12 x2 plus a13 x3 plus dot 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 going all the way into a1 n xn for n variables, and now you go down. Now these systems, I'm going to actually write out 3 of these so it's actually clear, because most of our systems will be 2 by 2 or 3 by 3, but this is scale to any number of equations and variables you want or need for your application. So just continue the pattern. A2n xn, we need the third one fully written. So x1 plus 32 x2 plus a3 3x3 plus 1 2 3 plus a3n xn, and then it's going to go down to xm, which is a m1 x1 plus a m2 x2 plus a m3 x3 plus dot dot dot, and here is the last term, which is mn xn. Now what you see here is our either 3 by 3 system, or in the blue box 2 by 2 system, and those are the ones that we generally use in class. Now some applications we call for more of these equations, more than 2 and 3, right? So depends on what you have. Now you can, let's say if you have, let's say you are some kind of chemical engineer and you're designing some synthesis process or whatever, and you need to mix a lot of ingredients in order for it to, you know, become whatever it is at the final stage of the product, and the system needs to go through 7 tanks of mixing with whatever stuff you are adding into those tanks. So then you will have 7 equations, right? Because those are the 7 different instances of mixing, and the change in concentration or whatever you're measuring, right, will be changing in each one of the tanks depending on the inflow and outflow of stuff that you are mixing solutions. So you could very easily find the application in what you would call the real world, right, where you can have multiple system with multiple equations, more than 3. So I just said, okay, have 7 things linked, and then do the mixing in each one of those. So the system like this would create that system that we said before, where you have your x prime equal to matrix A, right, times some value of those x's, and this is also a vector. So this is your vector of all x1 prime, x2 prime, x3 prime. And this is your x1, x2, x3. And this is all of your AMN matrix that you operate on. So technically, this is our problem here that we are solving. So it can be any size. We said it can be any size, and that's all we need to do. So how do we solve this problem? Well, we are going to assume, since this is, if you convert this into that good old day one equation, right, where you said, oh, but you know, if I have like dx dt equals to some constant a x, this is just a separable equation, right? Dx over x is equal to a dt, and then when I integrate both sides, I get ln x is equal to at plus c, and this eventually works out to be e to the a t, and then this constant, I don't know, call it k in front, it doesn't matter. But we see what the form of the solution looks like. And now, since that works for this case when you only have one variable and one unknown, and that's technically, guys, solving this. I hope that you see that we are just increasing and it stays the same. So the process should stay the same to solve this, because what we are doing now is we are doing this the same. We're working on the same problem, except we just have more variables and more equations. But the method of the overall solution should stay the same. So now, instead of expecting x equals k e to the at, we are going to say that we are expecting, right, our solution to have some kind of vector v solution, and then I'll write it in purple. We expect this x solution to be some sort of vector v e, and then we use this lambda, which is the Greek letter L, for the exponent up there. And now we just need to figure out what these things are. So we expect a solution of this form because, right, the 1-by-1 case that we studied in lecture 1 gave us that form of the solution. So this form definitely belongs in here if your vector v has only one variable and lambda is equal to this a, then yeah, that's the solution, right? And it belongs in this kind of a form. So now what I can do is I can replace all of these values and see what kind of a formula I get. Now this is a little bit of theory and derivation to see what I can get from here. So my x prime is equal to the lambda times vector v times e to the lambda t. And now we can stuff all of that inside our expression up there. So this mess goes here, this mess goes there, and then we come up with this equation of, so a prime is lambda v e to the lambda t is equal to a times v times e to the lambda t. Now, when you compare the two sides, you can see that the lambda v is equal to AV. And when you put these guys on the same side, so you move this one, you get a v minus lambda v equal to 0. And now you factor v, which is a vector. Now there is an issue here. So a minus lambda, I'll put I and then v equal to 0. Now, where this I came from? Well, this I is the identity matrix because a lambda is a scalar. It's a number, right? We know that because we are expecting this A to be, I don't know, 0.3 or negative 10, whatever. So this lambda is a constant. It's a number of some kind. Now, we're going to call that eigenvalue very soon. But for the purpose right now, we just know that that's some number. Could be 2, could be negative 2, could be 10, right? But it's a number. And matrix A is the matrix that contains, I don't know, square matrix of 2 by 2 or 3 by 3 and so on. So if you have a matrix that it's, let's say, 3, 4, 6, and negative 1, and then you subtract 2 from that, that makes no sense because we can only add and subtract matrices that have identical size. So 2 by 2 minus 2 by 2 or 3 by 2 minus 3 by 2, they have to be exactly the same in terms of their size in order for them to add or subtract, because that's done location-wise, right? A11 with A11. So if I multiply this with 1, 0, 0, 1, which is I2, which we discussed last class, then you actually have 3, 4, 6 minus 1 minus 2, 0, 0, 2. And now you can actually subtract. So this I over here is the identity matrix, and it technically just brings the dimensions to this lambda so that lambda can be subtracted from A, and it creates this equation, which is our equation that we are going to use to solve the problem. So now you have a matrix, a constant, a matrix, a vector equals 0. So yeah, so good luck deciphering all of that. Now in the book, they make matrices bold and capital letters, right? And the vectors get their, vectors are also bold but lowercase letters. Now it's easy for us to put the arrow. Now some people put, you know, a squiggle line like this above to, you know, say, oh, it's a matrix. There are other ways to denote this. Again, depends on what literature, what books you get to read. So now we need to learn what these things are. So we have this equation, and as I said, this is going to be the central equation that you will worry about. But then the other one, the form of this equation will be used to calculate what we call eigenvalues and eigenvectors, which together create eigenpairs. Holy nightmare, what are all these words? So let's go through all of that. So lambda is known as eigenvalue, and that is a German word, eigen, and it means something like the one. Okay, like Neo in well, actually, I always make this mistake. It's not, Neo is not the one in the Matrix, unless we'll see what happens in the fourth movie. So far, Agent Smith is the one, because he is the one that ticks all of the boxes of the prophecy being born in the Matrix, right? Neo was born outside of the Matrix, technically. Anyway, we'll not discuss the Matrix here. We'll wait for the fourth movie, see if that stuff clears up now that Agent Smith is... Well, actually, I don't want to spoil if you haven't seen. But then again, if you haven't seen Matrix 1, 2, and 3, I mean, you wouldn't be taking differential equations. It's like that and Star Wars are like prerequisites. Like, if you haven't ever seen those, then yeah, what the hell are you doing in this class? That's like That should be like one of the criteria. Yes, you passed Calc 2 and you have seen all of the basic movies, so you can call yourself a proper nerd. Anyway, so Eigen means like the one, right? And now you're going to have a vector V, which is going to be called Eigenvector. And that's pretty much, again, the same thing, like the one vector, right? And now the question is, what are these, right? And a lot of students just go through the whole linear algebra and maybe even score A in the class, and they still have no clue what this is and how to use it later on in engineering, which obviously creates a lot of problems. So we have to start with understanding that like what eigenvector and eigenvalue are. Now, eigenvector would be a vector that stays unchanged under a transformation. Now, vectors can be anything. Vectors could be constants. Vectors could be functions. Vectors could be trees, right? Now, I'm not sure if I can find an eigenvector for a tree, because generally when you apply a transformation to a tree, it doesn't stay the same tree anymore. For other objects and things, we could find an eigenvector because it would not, right? You would do the transformation, but the object would stay the same. We know that objects shrink and expand with heat, right? So that transformation would definitely change the object. But what if we have a material that when heated up doesn't expand? So we apply the transformation to it, we try to change that object, but the object did not change. In that case, that's the eigenvalue. So now you are entering the realm of understanding, oh wait, so superconductors, right? So now we're going to think about, this higher end science, which is not just, put two screws together to make something that works, the grabber, right? But you are actually designing something on a much higher level. Now, if you want a simpler example than that for mathematics, if I say that your eigenvector is e to the x and the transformation is integration, well, that thing stays the same. Or the derivative is another transformation on e to the x and it stays the same. Now, I know there is a plus c over here, but you can put the condition so that c is 0, and then there is no problem with the plus c. So when someone says eigenvalue and eigenvector, you're immediately thinking of whatever things they are, where they are staying unchanged under the transformation that is given to you. So now I gave you the example of heat as a transformation, and we know everything expands, right, with heat. I mean, let's take metals, right, or whatever. But then for mathematics here, I gave you an example of e to the x, right? So you apply integral or the derivative, which are transformations, because integration changes function into a different function, right? So you put x squared, 2x comes up, right? You put 1 over x, ln comes out. So whatever function you put into this integral transforms it into a different function. Well, e to the x stays unchanged. And in that case, e to the x would be represented as the eigen vector in this case, because it stayed unchanged under the transformation of integration. So eigenvalue and eigenvector are going to be these very special values for your matrix A, under which that vector under the transformation does not change. And obviously, I shouldn't be using that word, but obviously, that eigenpair, the eigenvector and the eigenvalue, would appear into the solution of this system because they are, I don't know, you want to call it a pillar or a pillar of support for the whole system. So the job of today's section is to learn the way to find eigenvalue and to find eigenvector and to put them in whatever way they need to be put together so that we can have our problem work. So let's go and take a look at the procedure. So for the procedure, I'm going to start with what I'm going to do is I'm going to first learn how to find eigenvalue. Now, to find eigenvalue, we are going to, well, let's write the definition, even though it's not probably going to mean a lot to you, because as I said, they don't use this language of, you know, explaining what these things are. They give mathematical definition and they move along. The number lambda is called an eigenvalue of the n by n matrix, provided that, and they give you the formula for it. So you technically learned nothing out of that in terms of application. Just told you how to find it, which is technically not a definition, this is a theorem. So the number lambda is called an eigenvalue of the n by n matrix A, provided that, and now here is a very similar equation to what we had earlier, except now it's determinant. So this is the way to find the eigenvalues, and once you have the eigenvalue, then you can find that an eigenvector associated with the eigenvalue lambda is a non-zero vector. That means you can't have 0, 0 or 0, 0, 0 or any of those. Those are not allowed. So it's a non-zero vector V such that and now we have the other equation, A minus lambda I times the vector V is equal to the 0 vector. So this is our life. All right. So this is a scalar 0 because determinant equals a number, and then right you solve that equation. And then over here is a 0 vector because now you have a matrix times the vector that gives you a vector, and that can only be equal to a vector, not a scalar. And now it's time for us to take a look at just the calculation for eigenvalue. I'm not concerned now with the differential equation. I just want to go in and find these values. So let's have the matrix A have 4, 2, 3, negative 1. 4, 2, 3, negative 1. So these are the coefficients. It's a 2 by 2 square matrix, right? And I just want to find lambdas, and I want to find vectors V, right? So that's all I want to do. All right, so lambda calculation. Come on, tablet. There we go. Lambda calculation. So lambda calculation is going to be the determinant of A minus lambda I equal to 0. This equation, when you compute the determinant, will give you an equation that you can use to compute lambdas. So now how you achieve that? Well, we plug everything in. You have your matrix 4, 2, 3, negative 1, and then minus unknown lambda times 1, 0, 0, 1 matrix, and then determinant of that needs to be equal to 0. So all I did is I just plugged everything in. Matrix A goes in A, lambda stays unknown lambda, that's your variable technically, and then you have your value for a 0. I mean for identity, and then equals 0. All right, so now what I'm going to do is work out this subtraction. Now lambda will distribute into these ones. So I have the determinant of 4 minus lambda, 2, 3, minus 1 minus lambda equal to 0. So again, 4 minus lambda is 4 minus lambda. 2 minus 0 is 2. 3 minus 0 is 3. And finally, I guess rainbow, negative 1 minus lambda times negative 1 is minus 1 minus lambda. So everything is accounted for, and you have your matrix that you have to find the determinant of. Now some books will say, determinant of 4 minus lambda. You know, if you go on YouTube, maybe research other videos and so on, you might find this notation as well. It's the same thing. Okay, whether you're going to put this absolute value parentheses, which mean determinant, or they write DET, which stands for determinant, depend on which book you read and what. Now we use this in class, but the other one is also very frequent. All right, so now I know how to solve the determinant, right? Multiply this way, turn around, multiply the other way. So I have 4 minus lambda times negative 1 minus lambda, and then minus 6 equal to 0. Clearly, this will end up being some kind of quadratic equation, and then I can just solve that. So let's go multiply. That's negative 4 lambda, positive lambda squared, minus 6. And lambda squared minus 3 lambda minus 10 equals to 0. So once you solve the determinant of this matrix, you come up with this equation that will spit out 2 lambdas, right? Because it's a quadratic. Now remember, those lambdas could be distinct, could be repeated, or could be complex, which will obviously give us a different type of a headache every time, with repeated one again being the worst of the bunch. I mean, if you know trig very well, then you have nothing to worry about the complex ones. It's the ones that are repeated that always makes the most noise, even though trig ones are the nastiest looking. But again, if you know trig, it simplifies very nicely into some solutions. So repeated ones are the nastiest, and I don't think they're not in this lecture. I think they're in 6.4 or 5.4, sorry. So we'll see them later. Anyway, so I have this one to solve. This is a lambda, not an x. Be careful with your notation. And now we have negative factors of negative 10, right? So that's going to be negative. So let's see what the negative 10 factors into, right? It's 1 and 10, and then 2 and 5. So how do I make negative 3? It's negative 5 and positive 2, would make -3. So I have a lambda plus 2 times lambda minus 5 equal to 0, and lambda equals -2. That's my first eigenvalue, and the second eigenvalue, lambda 2, is +5. So all of this mess just to find eigenvalues. Now, the second part of calculation is to find eigenvectors associated with each of the eigenvalues. So now there are going to be two separate calculations, one calculation for -2, and then repeat the same calculation for 5. All right, so now when lambda 1 is equal to -2, I'm supposed to solve that problem now with parentheses, if you remember where we had that a minus lambda I times vector v is equal to a 0 vector on this side. Okay, we already know this. It's the same like the one we had up there. So this is now the basic matrix. It's not determinant. It's a basic matrix of 4 minus lambda. I believe it was 2, 3, and -1 minus lambda. I have to verify that. Four minus lambda 2, 3 minus 4 minus lambda 2, 3 minus. Good. All right. So we got this. Now, vector v is going to be given, right, as a 2 by 1, what we call a column vector, right? And your 0 vector is going to have 2 zeros inside. So remember, vector v cannot be 0, 0. This one is always 0, 0, or 0, 0, 0, or 0, 0, 0, 0, depending on how many dimensions you have, how many equations you have. Always. So your 0 vector is always full of zeros, and your vector v is forbidden of being a 0. Because if it is a 0, guys, it's a trivial case. I mean, what is the purpose of transforming a 0? You can't transform it. Multiply, divided by anything, it still stays 0, right? So you can't really change if you're right, the integral of 0. Well, integral of 0 is 0. Derivative of 0 is 0. And it's a trivial solution. So that's why we're not looking for vector v ever to be 0, 0, because it's not something that you would be transforming. You don't transform nothing. There has to be something to be transformed. It's a different thing if you are building stuff, right? So you have no apples, and then someone gives you an apple. You didn't transform apple into a pie or ate it or left it to rot. I don't care what it is, right? You didn't transform the apple. You gained the apple from someone. That's not transformation. So you having 0 apples, right, does not transform into 10 apples. You can gain 10 apples. That's a different concept. Transformation and addition and subtraction, it's not the same idea. So we do not look for 0, 0 eigenvectors because they don't have, as I said, it's a trivial solution. There's no transformation happening there, so we don't care about them. Okay, cool. So now we are going into to plug everything in. We have that lambda is -2. So I'll have 4 minus -2, and then 2, and then 3, and -1 minus -2, and then my a, b, and my 0, 0. So I plugged everything in. And now let's write out the system we get. Well, let's write one more. So this is a 6, 2, 3, and 1, and then a and b, and then 0, 0. You can use these ones as well if you want to. Doesn't matter. Just you can't use the ones that are straight lines, the absolute values, because that means the determinant. But whether you're going to put these or these, I don't care. These ones you can't put. That's the drill. All right, so now we know what to do. Put a and b on top of 6 and 2. You get 6a plus 2b equals the top 0. And then you have your 3a plus b equal to bottom 0. Now, those of you good with the systems, you already see that this is the same equation. And that's actually what lambdas will do to this system. Lambdas will always, with all capital letters in the word always, make this happen. That one equation doesn't really matter. So you can just strike the top equation because it has larger numbers and just focus on the bottom equation to come up with your solutions. Now, the beautiful thing about this is that any vector that you possibly, any a and b that you can possibly think of to make this work will be the solution, and you will keep it as the answer. So when I have this equation here, I see that b is equal to negative 3a. I could have gotten the same conclusion from the top equation, right? So this is something that I was interested in, and now I say let a be 1, and then b is immediately negative 3, and there is my eigenvector 1, negative 3. It's as simple as that. So your eigenvalue, and if everything is computed correctly, it will always give you this situation where all of the equations give you the same thing. And then you pick one of the equations, solve for whatever variable you want, assign a number to the other variable, and compute the first variable you've done. Let's repeat that process. Oh, by the way, so now if I write lambda 1 equals negative 2 and v1 vector equals 1, negative 3, together they make what we call an eigenpair, right? Which is eigenvalue and eigenvector together. Now we rinse and repeat, but now lambda is 5. So we have our matrix of 4 minus 5, and then a 2, and then a 3, and then minus 1 and minus 5 times AB equal 0, 0. Again, you can use these, whatever. What I have here is 4 minus 5 is negative 1, so negative A plus 2B is 0, and the bottom equation is 3 minus 6B equals 0. Well, divide the bottom equation by 3 and you get the same numbers, I mean negative 3, and you get the same numbers as above. So we don't have to mess with that one. Now, from the first equation, you get that A is equal to 2B. Let B be 1, which immediately makes A to be 2. And there's your eigenvector V2, which is now 2, 1. Just make sure that you put B on the bottom. That's one of those facepalm mistakes, noob mistakes on exam where you are, so stressed and you're rushing and you're not thinking. The B is the bottom entry in the matrix. So make sure you put B down there. So now you have your second eigenpair, which is 5, and a V2 vector is given as 2, 1. Again, pay attention where you put your 2 and where you put your 1. And there you go. So that was the procedure for us to find eigenpairs. And before you say, who cares? Well, let's define what the differential solution to differential systems, differential equation systems, let's define it what it is. So this is a major theorem, obviously. So let lambda be an eigenvalue of the first order, well, of the matrix A of the first order linear system dx dt equals ax. Now that's our, we had that before a year ago, right there. Except it was not written as dx dt, it was written as x prime. Same thing. So that's our system. You already seen that system could be transformed, right? If you just have one entry, if you don't have a matrix A over here, but if you just have, let's say, number 10, and then just x, one variable, then the whole thing becomes a basic separation of variables from first lecture of our course. But this notation here allows you to have any number of equations, any number of variables, which is great. And now we say if a vector v is an eigenvalue associated with lambda. So if vector v is an eigenvector associated with eigenvalue lambda, there we go, then, and here comes the $1 million thing, solution x of t is given as a vector v times e to the lambda t. And that's why we bother with lambda and v, because once we find them, we just write the solution out. There's no integrating here, no differentiating. You're solving a quadratic equation, and you know how to factor. Like that's the extent of your troubles. So now, what would the solution actually look like, right? Because I had that matrix A to be 4, 2, 3, negative 1. And then we found those two eigen pairs. Now, where this matrix came from? It came from a system, and you can call that system, if you want, x prime equal to 4x plus 2y. Y prime equals 3x minus y. Do we all remember this system from last week? Right? We had these systems all over the place. And we transformed them and we did, right? But now I have a way to quickly solve this. Well, relatively quickly, right? What I have is I found that there is a lambda 1 was negative 2, and the associated eigenvector v1 was 1, 3. Was it? 1, negative 3. And we also found lambda 2 to be 5, and then v2 to be 2, 1. So we were able to find these eigenpairs for the matrix A, and matrix A came from this system. Now, by the theorem above, it says that this solution here is the solution for your problem. So now my solution x is going to be c1 vector v1 e to the lambda 1 t plus c2 v2 e lambda 2 t. And I have my answers here. Now let's plug all of these things in and see what the solution looks like. So my solution x vector, now guys, this x vector is xy vector like that, right? So when I put x with the arrow on top, that's a column vector that has xy, maybe has xyz, or maybe has x1 and x2. It's, you know, whatever all of the variables are. So I have c1 v1 e to the negative 2t plus c2 2 1 e to the 5t. And now this is what I can do. I can replace this. Well, actually, I can replace it here because we know that's that, right? We have now one-to-one correspondence of what, you know, what we plugged in. That should be clear between the two rows. So now, when I have this value, all I need to do is to have a row for x, and then a row for y. So you just follow the blue path, and you say x of t is equal to c1 e to the negative 2t plus 2c2 e to the 5t. And then for y of t solution, follow the blue flow, which is c1, oh sorry, negative 3 c1 e negative 2 plus c2 e to the 5t. So you follow the blue path, and you follow the green path. So all of these vectors, right? So x will always be all the tops, and the y's are always all the bottoms. And then the non-vector entities, like the c1, c2, and then e's, they are shared between all of them because they multiply, right? You know that if you multiply c1 into this, it's a matrix, but it's also a column vector. It's all the same. If you multiply this c1 into this vector, it will multiply into every entry position. So you're getting c1 and then negative 3 c1. And you can see that in the solution below. We did zero calculus. We did zero calculus here. You picked off your variables, your values. You made your matrix A. You went through the hoops to get lambda and this. We did not integrate. We did not differentiate. We literally did zero calculus. Like if these concepts were not, you know, on the eigenvalue and had the whole spiel of these transformations and things in the background and the linear algebra, I mean, you can teach this to a 9-year-old because they know all of the operations that are involved in this calculation. But again, there is much more to just, you know, mechanically solving this. It's like, yeah, but what does it mean, right? And the book does give you a 3-tank mixture problem, where they show you how these systems evolve from the word problem into the matrix that we just had. And I think it's a worthwhile mentioning this problem because you have, right, let's say you're a chemical engineer, right? There is a reason why, you know, some of them start at 80K start salary, or 85, whatever. So you are dumping whatever into this tank, it's getting mixed, and then you are going to, through the spigot, dump some of that stuff in here. It's getting mixed. Another pipe, spigot, whatever, it's going to dump stuff in here, and then obviously you are taking your product out into whatever. So each one has whatever solution is mixed at, blah 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 blah. Talk about the concentration, which is right what we care about. So the change of concentration for the first one is just right, because again you're adding, usually you're adding water, you're diluting the solution. So since you're adding 0, the only thing that you worry about is, let's say, the salt, right, or whatever mineral, I don't care, right? It's, you're mixing a red solution with a purple solution, and that's whatever. One of those two solutions is getting diluted, and it's dripping into the second tank. So you have your concentration of, let's say, salt in the first tank to decrease, right, with the rate of outflow of the water. Now, what's happening with the change of concentration in the second one? Well, this is tank number 1, tank number 2, tank number 3. So now K1 X1 is a gain that's coming in, and what's going out is K2 X2 going into the third tank, and then the third tank has the inflow of K2 X2 and the outflow of K3 X3 going out. So now when you take a look at this situation, you do have your matrix A clearly, dare I say, clearly stated: -1 0 0, 1 -1 0, and 0 1 -1. There's your matrix A. And now just go ahead, eigenvalues and all of that, all of the bells and whistles, right? You quickly come up with all of those things. So it's not far from your everyday job if you are the actual engineer, right? The ones that design and build things, right? Not the ones that sell, but the ones that, right? Who ends up in sales? Those who went through the education for a grade. They never learned anything. They don't know how to use any of these things to develop systems. So they are not the material that makes 80K, 90K, right? They are actually becoming a salesperson for 50, if lucky, right? So knowing these methods and how they apply in the situation, in this case, chemical engineering. Guys, I can replace this with springs. I can replace this with RLC circuits for electronic. It doesn't matter what application, right? It's just, this is what it's used. If you can come up with a system, right, the eigenvalues will solve the system. And that's not your purpose as engineer to solve the system. Computer does that. You know, you buy a $300 computer. Your job is to understand just this, to understand this, how to model, because that's the only thing that the industry needs. Other than that, you're completely useless. It's because the computer will always be able to solve these things much faster than you do. So let's take a look at one full system solution. Now the problem is that they don't separate these, so I'm just hoping not to run into a complex one, because if I run into complex eigenvalues, then I'll have to go through the complex. I mean, it is the part of this lecture, but I kind of wanted to introduce it before. Let's see how lucky we get. I'm just gonna pick a random one, problem 4, whatever. So it has x1 prime is equal to 4x1 plus x2, and x2 prime is equal to 6x1 minus x2. So that's our system. Now note that they are using x1 and x2. They're not using x and y. It doesn't matter, right? But that's that's a little bit different. So what is my matrix A? Well, that's just the front coefficients. 4, 1, 4, 1, and 6, -1. That's it. Those are our numbers. And now we unleash the procedure for eigenvalues. 4 minus lambda, 1, 6 minus 1 minus lambda. And we need to find the determinant of that and set it equal to 0. So 4 minus lambda times minus 1 minus lambda, that's 4. Let's write it still. Let's write it one more time. There we go. Wait, was this the same as the previous one? Because I'm getting the same values. It is the same. What? Whatever. So we're going to end up with the same numbers. The vectors are going to be different because we have a little bit different values, right? We have 1 and 6 rather than 3 and 2. So eigenvectors are going to be different. But at least lambda is the same deal. Okay. Whatever. So it was lambda squared minus 3 lambda minus 10, I think, was equal to 0. And then lambda plus 2, lambda minus 5, and lambda is -2, and lambda is +5. This is terrible because now you're going to think there are only 2 eigenvalues possible, -2 and 5, which is not true. Eigenvectors. So when lambda 1 is -2, my matrix now is 4 minus -2. Was it a 1 or a 6 here? 1. 1. And then we have a 6 over here, and this one was -1 minus -2. All of that needs to be multiplied by a and b, and to give us 0, 0. So that's 6, 1, and then 6, 1 again. I hope you see that. Right there. And now you are dealing with 6a plus b equals to 0. B is equal to -6a. So let a be 1, then b is -6. And you have your associated vector v, v1, which would be 1, 6. Rinse and repeat for 5. See, the vector is different than before, right? We had, I think, 1, -3 as a vector. And now we have 1, 6 as a vector. Oh, by the way, you could have said let a be, pi squared, in which case your b would be -6 pi squared. It's still an eigenvector, right? You can literally pick anything for your a and then compute b using the formula, because it's not what value they are, it's what the relationship between them is. This is the important part, because you are allowed to pick any number here. Now, the fact that I will hate you personally if you pick anything else by 1, because then I will have to redo all of my calculations just because you picked, 7, that's a different story, right, for grading. But the numbers are not important. It's the relationship between the numbers that it's important. So that's the part. Okay, now lambda 2 is equal to 5. Then you have 4 minus 5, and then 1 and a 6, and -1 minus 5 times your a, b equals 0, 0. Here is skipping like 30 steps now, because I just take a look at the top, and that's -1, 1. So -1, 1. So a is equal to b, and then just 1, 1 vector is perfectly fine. So I have my x of t solution as a c1 and then 1, 6, and then e to the negative 2t, plus c2, and vector is 1, 1, and e to the 5t. Now, what are my, now they want x1 and x2 solutions. Well, again, you go upper branch, and then you go the lower right branch. So x1 solution as a function of time is c1 e to the negative 2t plus c2 e to the 5t. And the x2 is 6c1 e to the negative 2t plus c2 e to the 5t. And this is our solution. So you would box this. Now, for my MATLAB, just I don't know which one is the one that they want, right? So, you know, if one doesn't work, then the other one is the one that they want. Clearly, if my MATLAB gives you x1 equal to and x2 equal to, then they want the one on the bottom. So just, you know, explore that. You might have to redo a problem. No, actually, it asks you, it lets you plug in 3 times, right, before they switch the problem. So, yeah, you should have enough tries to explore that. Cool. That's it, guys. So that's that eigenvalue. Now, how about if we have 3? Well, it's just more calculation. You know that your determinant for the 3 vectors is harder to obtain. So yeah, good luck there. And then you would have to find 3 eigenvectors. So now let's do one that it's 3 by 3. I'm already dreading it, obviously, but let's do it. And the thing here is that you are, where am I? Okay, 3 by 3. 17 through 26 are all 3 by 3 systems. So literally whatever. Here, problem 18. x1 prime is x1 plus 2x2 plus 2x3. x2 prime is 2x1 plus 7x2 plus x3. And x3 prime is 2x1 plus x2 plus 7x3. There we go. Right? So this is what we have. And when you now look at this, you get your matrix A immediately as 1, 2, 2, 2, 7, 1, 2, 1, 7. Right? That's your matrix A. And the procedure for this is always the same. You are going to multiply lambdas. Oh, sorry. You're going to subtract lambdas on the main diagonal, principal diagonal, and then you're going to find the determinant, set it equal to 0, and come up with 3 lambdas. And I'm just hoping that, again, no complex ones. We'll see what happens. So absolute value, 1 minus lambda, 2, 2. 2, 7 minus lambda, 1. 2, 1, 7 minus lambda equal 0. Now, this is not a 0 vector. This is equal to 0 because this mess on the determinant is going to end up being some equation of lambda, lambda cubed, and then that's equal to 0. All right, so now what? Well, we know how to find the determinant for 3 by 3 matrices. It's long, it's painful, but hey, such is life, right? So we pick the first one, 1 minus lambda, delete the row and a column, and do the 2 by 2 determinant there. So that's 7 minus lambda times 7 minus lambda minus 1. So that's that. Then we move on to the second, so that's -2. Remember that the determinant for the second one is a minus there. Delete row and a column. So now we have 2 times 7 minus lambda minus 2. So that's when you go like this and you come back the other way. And finally, we have our third, which is +2, and rho minus lambda. So that's going to be 2 minus 2 times 7 minus lambda. Equal to 0. So what is your life now? Your life is foiling, right? So now you foil everything over here, and that will all combine into some kind of lambda cubed blah 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 equal to 0 equation, right, in about an hour or so. So let's go. 1 minus lambda, and over here I have this square of binomial, so that's obviously 49 minus 2 lambda plus lambda squared, and then we have -1, which we need to deal with. Over here we have -2. Now I have 14 minus, see this 14? Minus 2, that's 12. And then -2 lambda. And then I have plus the next row, 2. Again, this is -14, so that's -12 plus 2 lambda when you distribute that negative sign. So -2 times negative lambda is +2 lambda. Usually this is a massacre on the exam because you are not paying attention to the signs and double up, triple up, negative signs, especially if you don't know determinants very well. If you didn't take Calc 3, didn't take linear algebra, then you don't technically have that habit of making this one negative, because it goes plus minus plus when you're working on the determinant. I'm not going to go into the proofs of that, right? But usually that's where, you know, your problems start, and then doubling up with negative signs and all of that stuff is just more of that mess. This 49 minus 1, that's 48, right? So technically what we have over here is lambda squared minus 2 lambda plus 48, because now I need to distribute this into all of that mess. It's going to give me 6 terms and then plus all of that stuff. So 1 times this stays the same, so that's a lambda squared minus 2 lambda plus 48. And now minus lambda minus lambda cubed minus lambda cubed plus 2 lambda squared, right, when I'm multiplying. And then minus 48 lambda. And then we have minus 24 plus 4 lambda, and then minus 24, and then plus 4 lambda equal to 0. And just collect the like terms, right? And if everything was done correctly, we should not have problems. We only have 1 lambda cubed, so that goes first. And then we have all the lambda squares, which is just plus single lambda squared. And then we have single lambdas. This one, this one, this one, this one. So that's 8, makes that 40 minus 2 minus 38 lambda. And all I'm left with are the numbers. And the numbers are minus 24, and plus 48. They cancel. I don't have any other numbers.
It should be minus 42 lambda, because -2 plus -48 is -50 plus 8 is -42.
You are saying this is -42. Uh-oh. You said -2. Oh, yes. This is a negative. I took it. Okay. Yeah. Well, thank you. Okay, that fixes a lot. That's great. Good catch. So now, when I do this, I'm going to kick out negative lambda, which leaves me the lambda squared minus lambda plus 42. And this now works beautifully, right? Because 42 is 6 times 7, right? So we have negative lambda, and then I have a lambda minus 7, lambda plus, oh no, the signs are opposite. Ah, 42, 1 and 42, 2 and 21, 3 and 14. 4 doesn't work, 5 and 6 and 7. Do I have another sign mistake somewhere? This is so close. So that's a positive, that's a negative, that's a positive. Can't factor this, guys. I need this to be a negative value so that it works out nicely with 6 and 7. Or I need the coefficient of lambda to be whatever these numbers add to. So now that it's this close, you know, I want to think that there is arithmetic mistake somewhere, apart from one being pointed out for the 42 over here. Because this is not going to factor nicely otherwise. We can try negative b plus minus square root of b squared minus 4ac. So that's going to be 4ac minus 4 times 42. Like it's short even to be beautiful for complex. Because 4 times 42 is negative 168. And when you do minus, you get negative minus 167. You need negative minus 169 for 13i. So like this is falling short from being okay for any of the solutions, and it's like really close. Like I need this to be a plus, and then it's gonna be working nicely, right? Because in that case, its square root is 13. And if you see that 13, then you get your 6 and 7, because 13 plus 1 is 14 divided by 2 is 7, and then 1 minus, right, you get your negative 6. This sign here is killing us right now. Like, really killing us. And to be honest with you, I have no clue if I can find it. I mean, usually you never find a... Going back to the book, looking at problem 18, and they all have plus signs. I have all plus signs. My matrix is 1, 2, 2, 2, 7, 1, 2, 1, 7. 1, 2, 2, 2, 7, 1, 2, 1, 7. Good. Subtract lambdas on diagonal and then go through calculations. So 7 minus lambda, and then minus 1 times 1. Minus 2, 2 times 7 minus lambda, minus 2. Plus 2, and then we're doing it here. That's 2 times 1 is 2, minus 2 times minus lambda. Holy nightmare. So FOIL this, that's a 49 minus... there it is. This over here is 14. I'm about to start crying right now. That's a 14, which changes stuff in here. So 1 times all of this is now 14. And then minus lambda cubed plus 14 lambda squared. And given that everything else is correct. So lambda cubed. So now I need to redo all of this stuff, and then we're hopefully good. Lambda squared. So what are my squares? This one and this one. So that's 15 lambda squared. Now singles or linears.
It should be 54.
What happened?
Should be negative 54, I think.
Negative 54 what?
Lambda, negative 54 lambda, I think.
Oh, you were giving me the answer for this. Okay. Yes,
Yeah.
negative 40, negative 54 lambda. Okay, thank you. Yeah, for a moment I said I thought you were talking about this. Okay, negative 54 lambda. Cool. And then these guys still cancel. All right, good. I think we are in good shape now. Let's see. Kick out negative lambda. That's going to be lambda squared minus 15 lambda minus 54 equal to 0. Now, factors of 54. It's 1 and 54, 2 and 27. What happened?
Negative. Is it plus 54 because you took out the negative?
Da, 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 da. We should end the class if I can't keep any of these things straight anymore. Thank you. 3 goes in 1, 24, 18. Oh, that makes 15. Okay, cool. There we go. Wow. So negative lambda, and then lambda plus 3, lambda minus 18 equal to 0. So lambda 1 is 0, lambda 2 is negative 3, and lambda 3 is positive 18. Wow. All right, well, that was a nice 20 minutes just to get lambdas from this mess. I made only 4 mistakes on this one. which means that my problem is long gone. All right, so now when lambda 1 is equal to 0, we stuff that lambda into each one of these. So we are technically getting our original matrix back, which was 1, 2, 2, 2, 7, 1, and 2, 1, 7. And we are multiplying that with ABC to give us 0, 0, 0. Now, if you don't know row reduced echelon form from linear algebra, this becomes a little bit of an issue, right? Because we're supposed to be able to get one of those equations eliminated. Now, there is a row reduced echelon form for your TI-8384 calculators, which is something that, you know, we'll see. Let's see what we can get over here. To work this out, 1, 2, 2, 2, 7, 1, 2, 1, 7. I'm going to eliminate, let's say, these guys. So I need to multiply row 2 by -2 and add that to row 1, and that would eliminate this one, and the one will become 0. Now, in a separate calculation, I need to multiply a row two by -7. Oh, this looks like x minus 7. This is times. So multiply by -7 and add that to row 3, and that will kill this 7 and make it a 0. All right, let's go and see what we get. So the new matrix is 1, 2, 2. No, arrow. There we go. 1, 2, 2. Now, when I multiply this one by -2, I get -4, plus 1 gives me -3. 7 gives me -14, so that's -12. And then gives me -2 plus 2 is 0. So again, the way I'm doing this is -2 times 2 is -4, and then I add 1, which gives me -3. And then I repeat the same thing. 7 times -2 is -14, add these two, -12. And again, that's all collateral damage, because we were focusing on this calculation here. -2 times 1 is -2, plus 2 gives you 0, because we are after this 0 here. Now, the rest, changed, but it had to change. I mean, we can't control that. So now I have my second row, and now do the same thing for the third row. I'm multiplying the top row by 7, -7. So that's -14, and 2 is -12. And then I'm multiplying the bottom one by -7, and then the 7 and the 7 up there will give me 0. No, that's -49. What am I talking about? 7 times -7 is -49, plus 1 is -48. And 1 times -7 is 7, so that's a 0 that we were looking for. There we go. So now we have all of these ends over here to be 0. All I need to do is to make a 0 here, and but I think you already see that if you multiply this row by -4, you get the same as the bottom row, so they all subtract to 0. Right? So if you multiply that row, you get 12, 48, 0, and then -12, -48, and 0. And when you add them, you get 0, 0, 0. So what is my matrix? My matrix is 1, 2, 2. We can divide this row by 3 to simplify it. So you with -3. So you get 1, 4, 0, and then 0, 0, 0. There we go. Now, when that is multiplied by ABC to give you 0, 0, 0, you have your A plus 4B is equal to 0, and you have A plus 2B plus 2C equal 0. Now, on the first one, your A is -4B. Let B be 1. And if B is 1, then A is -4. And now stuff those into there. That's a bad arrow. This one and this one go into this equation. And then you get your -4 plus 2 times 1 plus 2C equal to 0. So 2C equals 2, c equals 1. And there's your vector. -4, 1, and 1. That's v1, by the way. Now we rinse and repeat when lambda is whatever other numbers are there. And yes, these problems do take forever. So, and you have to be extra careful, right, not to mess up like I did 4 times just to calculate lambda. Luckily, I did not have any problems here. So now lambda is -3. Yeah, we're not going to have time for complex values. We'll have part 2 of this lecture. So when lambda 2 is -3, we go on a diagonal, and then, right, so this is, and lambda is 0. So that's my Eigen pair. So when lambda is -3, right, you kind of see that this is not like the, exam material like this 3 by 3 and 4 by 4, unless, all of this simplifies much faster and you don't have to go crazy. So what was my lambda? Was -3. So that's going to be 422. 422. -3 again. 422. -3 is 10. So 210, 210, 210. Okay. 210. 1 and then 2, 1, 10 times ABC equals 0, 0, 0. Again, row reduce echelon form. Row reduce it to get these into zeros. That will eventually make this 2 to be a 0. And then you pick your values and you go from there. So let's do this procedure one more time. And then the third eigenvalue, eigenvector will be, I guess, your homework, and then you can just write out the solution. So 4, 2, 2, 2, 10, 1, 2, 1, 10. I like to space these out so I can see exactly what I'm doing. This is going to be times -2 and added to the first one, and then times -10 and added to the second one. Now, you don't have to multiply by -10. You can just multiply by 10 and subtract 2 equations. I mean, it doesn't matter which way you do this. So what is the matrix that I get? When I multiply by 2, -2, I get -4. Oh, first I copy the top equation. I'm not changing that one. Now, for the bottom equation, when I multiply by -2, I get -4, and +4, I get a 0 here. Then -20 plus 2 is -18, and then -2 gives me the 0 I was going for. And then the bottom one is times 10 on the second row combined with the bottom. Okay, so times 10, that gives me -20, so gives me -18 over here. And then the second row times -10, that's -100. -100 plus 1 is -99. And then we have -10, then we have a 0 here. I don't like it. So -3, that's a 422, 210, 1, 2, 110. 422, 210, 1, okay. So times -2. -4, -20. Something might be off again, because I'm not getting a row of zeros. Let's try it. I mean, if B, if B is equal to -18, right, then -18A minus 99B needs to be equal to 0. So that's going to be -18A minus 99 times -18, because B is -18. So now, if I cancel by -18, then A is 99. And now I pick C. That's 4A plus 2B plus 2C to be equal to 0. 4 times A is 99, plus 2 times B is -18, plus 2C equal to 0. I'll cancel the 2 everywhere. And I get 2 times 99, that's 198, minus 18 equals minus C equals to 0. No, plus C equals to 0. So this is 180. So C is -180. So would this work in all equations if I have them as 99, -18, and -180 as a vector? So pick the third, let's say. So 2 times A minus 1 times B minus 1 times B, which is -18. And then plus, no, it's plus 1. So 2 times 99, 1 times B, and then 10 times plus 10 times -180. That's not going to make a 0, right? So there is still something wrong. Oh, this is awesome. There is a mistake somewhere. I mean, I know immediately when this doesn't work out that something is wrong. It's just, now we got to go back and figure out what's wrong. And it could still be something wrong with our lambda calculations. Because, yeah, we did get nice numbers, but for some reason the values now is not working out. When you pick this -3 and negative, oh my god, I still didn't factor it correctly. I didn't factor it correctly. I can't use negative and positive here because that's a positive 54. They have to have the same sign. Is this divisible? This divisible by 6 and 9. And that makes 15, and both of them are negative. Stupid. So -6, -9. That's why the other one worked out fine, and this one is not working out, because I have wrong. I can't do algebra. And this is actually what I did the whole morning in algebra class. 9 to 11, I did this with students for an hour and a half. And now I am I am messing it up. It's It's minus 6. So now all these numbers are off, which are these numbers. And then all of this now obviously doesn't work. But at least now we're going to get it right. Yeah, the class ends exactly now, but if you want to stay extra, 10 minutes to see this, I'm just going to extend the class and do this one, and then you follow the same steps for -9. Yes?
Wouldn't it be factored as -x? When you're factoring, you got, yeah, so then it should be +6 and +9. You have -6, -9.
Yeah, I'm mentally gone, man. You're right. I am so upset that I made these silly mistakes so many times that the problem is completely destroyed, and enthusiasm is completely gone as well. It's just frustrating. So we have 1 minus 6. We're using 6. So 1 minus 6 and then 7 minus 6. So 1 minus 6, 7 minus 6. And there it is. There we go. So now we see the same equation repeated. Same equation repeated. When I subtract these two equations, it's just gone. So I have 5, 2, 2, and then 2, 1, 1, and then row of zeros. Much better. And now if I multiply here by -2 and add equations, we have -5, 2, 2. And then when I say -2, that's going to be a -9 over here. 0, 0. 0, 0, 0, 0, I think. Right? Yeah. Good. So, I have equation -5a plus 2b plus 2c equals 0, and -9a equal to 0. So you can literally pick anything you want for a and a b. Well, a has to be 0. So from here you get that a is equal to 0. And you can pick anything you want for b and then calculate c. So a is pinned to be 0. You pick b equal to 1. And then you compute your c, because now you have 2b plus 2c equal to 0, because a is 0, so that kills the -5. And since b is equal to 1, you get 2 plus 2c equals to 0, c equals -1. Holy nightmare to get the second vector, because I can't factor. And but anyway, there's the second vector. And now the third vector, right, from lambda 3, which is 9, you will have, you go back to the original all the way on top, and now you subtract 9. So that's going to be -8, -2, -2. -8, -2, -2, and the rest of the values stay the same. So 2, 2, 2, 1, and 2, 1. So now you reduce this one the same way we did, and you will find the V3. So here, just do it. And then when you are done with that, you have your solution X to be C1 V1 E lambda 1 T plus C2 V2 E lambda 2t plus c3 v3. Now these are all vectors, right? So they get those 3. E to the lambda 3t. And when you write this out, this is a vector x. When you write it later on in x1, x2, x3, you get to write your, what was our v1? Negative 4, 1. So that's going to be negative 4 c1 e to the 0, right? So it doesn't get it because lambda 1 is 0. And then plus c2 had what as a? 0. So there is no term for c2 because of the v. And then you just get whatever c3 v3x value, whatever you get there, e to the 9 lambda, that one survives. Then you go to the next and next, and you will be able to write out all of them. I'm just gonna, put this because we did not calculate v3 yet, but that top, right, the 3, 1 value. I mean 1, 3. Sorry. No, what I'm saying, 1, 1 location. It's the vector 3, but it's a 1, 1 location at vector top location. So yeah, now we'll have to rinse and repeat for trig, for complex roots, and eventually we'll have to do the repeated ones, which make this mess of calculating vectors worse, actually, because you won't have enough equations, and it's just not going to work well the same way. So we'll have to figure the workarounds, right, to go around those calculations. But you know what? Everyone is fried and probably mentally exhausted by this point. So we'll pick it up on Wednesday, finish this off, and take a look at some pretty pictures in the next section. So we'll try to have part 2 of this mess, and then do 5.3 following this. I will see you then.